Good morning. Today I'm going to be talking about explaining the likelihood ratio in DNA mixture interpretation, and the goal is to demystify things a little bit. So, what is the likelihood ratio? Well, likelihood ratio is many, many things in most fields across science and social science. It's a standard measure of information. It's a single number that summarizes the support for a hypothesis. It's a way of accounting for all the evidence in favor or against a particular hypothesis or proposition. It's also the match statistic that's used in all DNA reporting, as I have a poster downstairs that shows. It's also, in many ways, forensic science's credibility in court, since it has good legal and scientific standing. In some sense, though, it's how does the data update our beliefs in a hypothesis? And yet, a quick show of hands might indicate that the likelihood ratio is not all that popular in the U.S. just yet for reporting DNA. I won't even ask. And there are several reasons. One is that forensic analysts outside of DNA don't have it available for most things, and that within DNA analysts sometimes find the LR hard to explain. However, since all DNA match statistics, including inclusion, are likelihood ratios, the stronger likelihood ratios can preserve the DNA match information, and the weak ones discard match information, so it's very helpful to know what the difference is if your goal is to preserve information. And without a likelihood ratio, you can misreport DNA that's highly informative as inconclusive. The approach is to find a better way to explain the likelihood ratio so that everybody in the U.S. starts using it because they're comfortable with it. Here's a quick history of the likelihood ratio. It was Thomas Bayes in the 18th century who first came up with the idea of how do you update your beliefs or probability based on data. How do you revise your hypotheses? In the 1940s, Alan Turing, the father of computer science, used likelihood ratios for the Enigma code breaking project. And Jack Good, who worked with Alan Turing, got this into more popular science and statistics with his classic book, Probability and the Weighing of Evidence. Chapter 6 is fantastic if you can just read it. It's written for scientists, not for statisticians. Dennis Lindley, in the 1970s, a Bayesian statistician in England, introduced likelihood ratios into forensic science in a rigorous way, starting with glass evidence. And his book, Understanding Uncertainty, is an amazing book written for lawyers, judges, non-scientists. That's a fantastic introduction to probability. And over the last 2 decades, John Buckleton, Ian Evatt, Bruce Weir, and others have brought the likelihood ratio into the interpretation of DNA and mixtures. I'm going to quickly describe 4 different forms of the likelihood ratio. You can ignore the math, but each has a different, and I'm not showing any proofs. That's in the appendix, I guess at the break. But these 4 different forms have 4 different ways of stating how you say a likelihood ratio. So here's the original form that came out 60 years ago in Jack Good's book, The Weighing of Evidence. It's the hypothesis form. It says the identification hypothesis, in our case, is that the suspect contributed to the evidence. And you start off with your prior belief about that hypothesis based on random people before you see the data. After you see the data, you update your hypothesis, and now you look at the odds of the hypothesis given that you've seen the data. In other words, what's the information gained based on the data? And a way you can state this in English, suppose that the factor was 1 billion, that's the likelihood ratio, I'll use that throughout the examples. You could say the evidence increased our belief that the suspect contributed to the DNA by a factor of 1 billion. Sounds like English. Now, this is the problem. Those of you looking at this, breaking into cold sweats, know this. Others of you are very happy with it, but many people aren't. This is a form that says, suppose there's an alternative hypothesis that someone else contributed to the evidence. You do what statisticians and computers love to do. You contrast hypotheses and say, well, that's easy. The likelihood ratio is the probability of the data, given the identification hypothesis, divided by the probability of the data given the alternative. And in English, you might say something like this: the probability of observing the evidence, assuming that the suspect contributed to the DNA, is 1 billion times greater than the probability of observing the evidence, assuming that someone else was the contributor. That's a lot of words for Americans. Brits are really comfortable with that. But in the U.S., you can't expect a jury who may be enumerate, math-phobic, and is used to short sound bites to process that. And therefore, we don't use it here. So let me show you 2 more forms of the likelihood ratio that are mathematically equivalent. First, if you know what a genotype is, and I'll describe this visually later on, you can say at the suspect's genotype, what was the information gained based on the genotype? Now that's starting to look, there's no conditional probability here, by the way, so you're not going to transpose anything, but it says what's the probability of the evidence genotype relative to a coincidental genotype. In other words, before there was a random population genotype based on the product rule. After you've seen the data, it was updated. And you might read that as, at the suspect's genotype, the evidence genotype is 1 billion times more probable than a coincidental genotype. Well, that's great if you know what a genotype is, and you have pictures, but maybe your jury doesn't know what a genotype is yet, and you don't have a picture. Well, this is the simplest form that is plain English, and they're all equivalent. This is the match form, and it addresses the question, how much more does the suspect match the evidence than some random person? What's the information gain, not in the hypothesis or in the genotype, but in the DNA match? People have an intuitive idea of what it means to match, and that's the probability of an evidence match over a coincidental one. And in English, that reads like, a match between the suspect and the evidence is 1 billion times more probable than a coincidental match. That's English. I think that's even more comprehensible than a RMP statement, random match probability statement. So I'm going to use this and illustrate it throughout the talk with some examples. Mixture interpretation is interesting because there's more than one possible allele pair on a list at each locus. And again, the likelihood ratio is evidence relative to coincidence, but different methods yield different DNA information. Let me give you 3 examples. Random match probability, when you don't have a mixture or there's a clear major, you write as 1 over the probability of a coincidental match from the product rule. What's the chance of seeing a match in the population? Inclusion, though, as we'll see in a minute, diffuses that probability over many possibilities, so you get a small matching genotype probability over the coincidental match. Quantitative methods can preserve more and give a larger matching genotype probability over a coincidental match. So let me show you what a quantitative method looks like for those of you who may not have seen one. This is data. You see that there are 2 alleles that in this case might come from a major contributor, 2 alleles from a minor contributor. And the question is, what are the underlying genotypes here? You're trying to infer major or minor contributors, or both. What most people in the U.S. use are qualitative thresholds. This is before stochastic thresholds, which would make that 3 times higher and make your data disappear. When you apply a threshold, you take the quantitative data and you slice away the information, all the quantitation disappears. You're left with, in this case, 4 all or none, hopefully allele events. And then all possible allele pairs, as you know, would be the 10 pairings of those 4 events. That diffuses the probability across 10 allele pairs and drops your likelihood ratio. Quantitative interpretation, instead, would try out every possibility of allele pairs, mixture weights, stutter, peak uncertainty, degraded DNA, like all good computer systems do, and generate patterns to compare against the data. When the quantitative pattern, assuming this major and that minor, and the stutter and so on, and the relative amplification fit the data very well, there's a high likelihood. When you propose genotypes, values of different allele pairs, maybe the wrong number of contributors, whatever, and you get patterns that have nothing to do with the data, you get no likelihood, which will give you no probability. And in between, you get things in between. And that's how computers, by doing a complete search and the laws of probability, can infer the probability distribution of allele pairs where they don't all have equal weight. So that's a quantitative method. You condition on the quantitative data, and you never change it, which is a no-no in statistics. You just use it and try to explain it mathematically. TrueAllele, which I wasn't going to mention, but I thought I'd tell you anyway since it appears in the examples, is a quantitative computer interpretation method. It does statistical search using a rich probability model with thousands of variables. The main one being that we care about is the genotype. That's what goes into the likelihood ratio. It preserves all the identification information, and it objectively first infers genotypes, stops, and never seeing a suspect, and only afterwards makes any comparison with one suspect, 10, or an entire country's database. It can use any number of mixture contributors, 4, 5, whatever. It has models for stutter, imbalance, degraded DNA, and all the things you're used to. Most importantly is it calculates the uncertainty of every peak. The reason this is important is that you don't have time in this talk, but I can tell you afterwards if you ask, is that if you know the uncertainty around every peak, then you know to what extent the patterns are comparing well with the data. If you don't work out the uncertainty, you may as well use thresholds, because you're just back to qualitatively trying to figure it out. So most of the research for the last 5 years after the live demo I gave here, I think 7 years ago, is on how you calculate the uncertainty at every peak. Think of it as a bell distribution, bell curve around every peak so you know exactly how confident it is. That's what lets you proceed. Those methods are about 20 years old in statistics. The system was created over 10 years ago. It's now in version 25. It's been there for 2 years. It's been used on over 100,000 evidence samples, and to dispel myths, you can have it as a product, as a service, product and a service, whatever floats your boat. This is the landmark case, Commonwealth versus Foley, which was the first case that we know of where rigorous statistical computer interpretation of DNA mixtures was admitted as evidence after a pretrial hearing and used in court. The original inclusion statistic was 13,000. Robin Cotton's obligate allele method gave 23 billion. TrueAllele gave 189 billion. How would you state this using the language? Well, you make your assumptions. You assume maybe there are 2 contributors to the DNA mixture, including the known victim, and this is English. A match between Mr. Foley and the fingernails is 189 billion times more probable than a coincidental match, in this case, to an unrelated Caucasian person. Again, looks like English. This is a recent case that I testified in over the summer of the Queen of England versus an arsonist. And there was a low template mixture with 3 DNA contributors. Triplicate amplifications were done with post-PCR enhancement. The peak heights here, if you account for the enhancement on ordinary pre-enhancement, are all under 50 RFU. And as you can see, the patterns are highly dissimilar because there's a lot of stochastic variation. If you have a computer, it spends most of its time working out peak uncertainty. It models it, tries out all possibilities. After no match score was found, the British did what the British do when neither man nor machine in England can do anything. They call cybergenetics, and we applied TrueAllele to it. This is perhaps the most important picture to take home in your mind. So here's locus VWA from that data we just saw. In brown, you're seeing the population distribution of the allele pairs based on the product rules, 2pq, p squared. And there's a little bit of what you'd see before you have the data. After looking at all the quantitative data, the computer updates its genotype belief. It changes its probability distribution from the population to whatever the data indicated. And that's shown in blue. So there was some gain, there was some loss. Now we don't know who the suspect is yet. Now we do. We take the suspect, we slide this window over it, land over here, and at this particular allele pair, we see that the posterior genotype probability is 6 times higher than the prior one. I showed this in a TrueAllele interface to the prosecutor, who then insisted on explaining it quite successfully using visualization like this to his fellow prosecutors and police without my intervention at all the other loci. He was quite pleased with himself. He knows no science or math, but this was completely obvious to him. visually. This is the genotype approach. And a statement looks like, well, assume co-ancestry with a theta value of 1%, and there are 3 contributors present. Then in English, you can say, a match between Mr. Broughton and the fuse is 3 million times more probable than a coincidental match to an unrelated Caucasian. Again, it's English, and it's mathematically correct. So scientists gather, and of course all they ever do is explain the likelihood ratio to each other, and other physical phenomena, the physics of helicopters, whatever's happening. LR methods vary, as Dr. John Butler from NIST has shown in his classic slide from 5 years ago on 2 contributor mixtures that were sent out to over 50 laboratories. There was a range from inclusion to more quantitative human methods, over 10 orders of magnitude of different likelihood ratios, match scores, on the same evidence. This is a study that we published last year in PLOS ONE. This is data from NIST, which was a series of known mixtures, 9010s, 3070s, and so on, with serial dilutions. Just look at the blue for a second. What you're seeing is here's the amount of unknown culprit DNA on a log scale, 10 picograms, 100, 1,000. And here on a log scale is the likelihood ratio, 1,000, million, billion, trillion, quadrillion, and so on. What we see is the computer interpretation using the method. The paper has 4 different methods. This is the one where it's a 2-person mixture. We assume the victim, solve for the unknown genotype. And what you see is down to about 100 picograms, you get all the match information, and then there's a linear predictable decrease down to a less information at about 1,000,000 to 1 likelihood ratio level. That's about 15 picograms. As expected, in red, this is the inclusion method. And what you see is that below 150 picograms, it's gone. You're not getting very much at all. And that's why with human review methods, people tend to not go much beyond 100 picograms. Computers don't have the same limitation. This is a study that's forthcoming in Journal of Forensic Sciences, done jointly with Dr. Barry Duesman in New York, showing how quantitative interpretation preserves the likelihood ratio information, whereas human review discards it. Here are 8 cases. Here again is the log likelihood ratio, 5, 10, 15, that's I guess quadrillion to 1. These were taken from the reported coded statistics from the case file. And what you see is on average the computer is preserving maybe 10 trillion, 10 to the 13th, whereas human review of the same data is 10 to the 7th, 10 million, and using thresholds relative to quantitation discards a millionfold, 6 zeros worth of information. Because all match statistics are likelihood ratios that can be explained in the same way, they can be compared, and you can do studies like this. More dramatically, Barry and I then looked at what happened when we didn't assume that there was a human review score that came out. We just looked at all 85 items. In blue in the background, this for the 85 items on the x-axis, still looking at information log likelihood ratio on the y-axis, this is sorted by information. You see the information obtained by computer. In the different colors, gray is RMP, green is CLR, and orange is CPI, you see for each of those cases what the human result was. They lost about 2/3 of the information where they did get an answer, but most tellingly, not even 30% of the items had any match score attached to it. That's an amazing statistic if you think about it. It means that if your goal is to keep processing items until you're lucky enough to get a match score, sort of like DNA Russian roulette, you have to do 3.5 times the work to get a number that'll be half of what you would have gotten had you used an informative quantitative calculator in the first place. The likelihood ratio also applies to investigative DNA databases. This is how TrueAllele, and I would suppose any other highly informative DNA investigative database works. The allele approach discards information. It's just like CPI. In fact, it is inclusion. You're listing alleles to give a very weak representation of the genotype probability distribution. It's there, it exists, but it's not very informative. It's making very poor use of the data. And so it's storing information poor genotypes and matching them. If you use probabilistic genotypes with more of the evidence, you can store and match those, and then when you have a new convicted offender or a new piece of evidence come in, then a likelihood ratio is computed, and you have the sensitivity and specificity that likelihood ratios are known for throughout science. With TrueAllele, we use evidence versus convicted offender match. When we redid the World Trade Center data, you showed we could use it for disaster victim identification. The same methods can be used with kinship to find missing people, and with TrueAllele, it can completely automate familial search. Automate meaning you don't do anything except let the computer solve it for you in the background. And we set this up so that it can be customized to each state and each country to its own jurisdictions, laws, and so on. The SWIG-DAM guidelines from 2010, paragraph 3.2.2, write that down if you will, says that if a stochastic threshold is not used, please use probabilistic genotype methods and validate them. And that can be useful because if we're already throwing out half of the evidence for mixtures because we can't put a number to them, and you triple your threshold, as some of you may have observed, you're able to report a number on even less evidence. Maybe it's down to 25% with your property crimes. But you can use probability modeling to preserve information, and you can measure the efficacy, of course, because all match statistics are likelihood ratios. So what is the point of forensic science? I mean, why do we do it? Or why do many of us do it? Certainly the public and the police view is that we want to preserve all the DNA identification information that's present in the data. We want to provide an accurate DNA match result. That would mean that if the number is 1,000,000,000 to 1, we report 1,000,000,000 to 1, not 1,000,000 to 1. And if the number is 1,000,000 to 1, we don't say it's inconclusive. The point is to serve the criminal justice system for law enforcement and the courts in an objective way to protect the public from crime. It's not to make ourselves feel comfortable. It's to bestow the benefits of science on the public, much as any doctor or engineer would when they are concerned about the safety of society and doing the most accurate job they can. Again, this is the sort of language that is English. No conditional probabilities, no transposed conditionals, no, sentences that go on for 50 words. A match between the suspect and the evidence is 1,000,000,000 times more probable than a coincidental match. So in conclusion, if you rearrange the math into an exact form that is one of the 4 forms, or 5, actually there are many, many forms of likelihood ratio, but not that probability of data ratio that's wonderful for computers and statisticians, but somewhat opaque to mortals, the likelihood ratio is easy to understand. And it's easy to explain in court. I do it all the time, and I'm having lawyers explain it to their friends. The point is you need to state it in the appropriate form. The match form is particularly nice. You always have the same denominator, the coincidental match, just like in the RMP. But in the numerator, the weight of the match of the evidence relative to the suspect, that decreases with weaker interpretation methods, and it stays high and is preserved with more informative likelihood ratio methods. And when you take the ratio, the information is preserved, which is one scientist's view of what the purpose of forensic science is. The slides for this talk, the handout, can be downloaded from our presentations page on our website. Actually, on our presentations page, every talk that we do, we try to not just have the handout, but also a transcript of the talk and a movie of the slides in case you want to see it again or tell your friends about it and show it when you get back home to your kids in your laboratory. If you are interested in getting some more papers, we have most of the manuscripts up on the website as well. If you want any information, email me, and I'd be happy to answer your questions. Thank you very much.